Welcome to another episode of the microprocessors course. In this episode, I will teach you the physical memory organization. We already know that this 8086 is a 16-bit microprocessor, means that it can handle 16 bits of data at a time. But most of the ICs are byte oriented. That means that each memory location contains 1 byte of data. In fact, the memory will be separately connected to the microprocessor. So here two memory chips will be used to store the two consecutive bytes. So the even memory will be saved at the even bank and the odd memory will be saved at the odd bank. That means that the entire memory of 1 MB will be divided into two banks. One is even bank and another one is odd bank. In even bank, all the memory addresses are even type, and odd memory bank will be the addresses will be the odd memory addresses. So in fact, this each memory location contains 1 byte of data. But here the microprocessor designed for a 16-bit microprocessor. That means that it can handle 16 bit of data at a time. In order to save the 16 bit of data at a time, we need to use the two consecutive memory locations. Means that let us take a value of 000H memory location. We need just save 12H. In the next consecutive memory location, we need to store another value 34H. So this is the lower significant byte and this is the most significant byte. If we are selecting the even memory, then we can use only 1 byte of memory cycle for a reading and writing operation. If we are selecting the odd memory address, then in one lower significant byte will be saved at the first and the next one is the most significant byte in the next consecutive memory location. Means that 2 bytes will be required to read or write the two memory cycles. So for even memory, we need only one memory cycle required reading or writing operation. But for in case if we are selecting the odd memory address, we need to use the two memory cycles for saving the lower significant byte and saving the higher significant byte. In general, the processor provides two signals like A0 and BHE bar. If we are using A0 and BHE bar in such a manner, by putting 00 and 01 and 10 like that, we can access the even bank or else odd bank, and you can access both banks to access the complete word or to transfer the complete word. So here I have already told you the entire 8086 microprocessor 1 MB memory physically divided into two banks. One is odd bank and another one is even bank. So each bank contains 512 KB each, addressed in parallel by the processor. Here the instructions generally coming from the memory to the processor. In the processor we have two units. One is bus interface unit and next one is execution unit. So the memory will be externally connected to the microprocessor. So in general the information will be stored into the memory. Here the memory chips are used two memory chips to save the lower significant byte and higher significant byte or 16 bit of data or opcode. So the instructions are coming from the memory in the form of byte or word. So in sometimes we need to store the data and sometimes we need to store the opcode. In other times both data and op will be there in the memory itself. For identifying the opcodes and data, the memory instructions are coming to the processor in the queue. In the queue, the prefetched instructions are sent to the decoder, internal decoder unit. In the decoder, what happened? The instructions are translated into sequence of steps. So what are the actions to be taken? That decoder output will be sent to the timing and control unit as in the form of input to execute the instructions. The bus interface unit takes 1 or 2 memory cycles for referring the word data by choosing a starting byte is located at an even address. So if you are choosing an even address as the starting address, then one memory cycle is enough. If you are choosing an odd address, 2 memory cycles are required to read or write the complete word. So preferably the people are always choosing the even address to transfer the entire word for reading and writing operation. So if you are choosing the odd address, the lower significant byte will be stored first and the next consecutive memory location will be read as a higher significant byte. That now we have discussed this thing. Let us see here the memory will be divided into two banks. One is even bank and other one is odd bank. This even bank is 512 KB each and odd bank is also 512 KB each. So each bank is divided into 512 KB each. So the even bank is nothing but even memory address will be saved here, and odd bank is nothing but odd memory will be saved. Odd memory address will be saved in the odd memory bank. So by selecting the A0 and BHE bar, when we are connecting this BHE bar, processor BHE bar is connected to the CS bar, means the chip select of the bank 1, and A0 from the processor pin is connected to the chip select for a bank 0 to access the bank 0 or even bank and access the odd bank. In some cases we need to use the two memory banks to access the entire word or in the byte. So this is the memory interfacing we have seen now to send the data of the D0 to D15 or D0 to D7 as well as D8 to D15 depending on selecting the A0 and BHE bar. Let us see the same thing here. BHE bar and A0 will be selecting 10. That means that read or write a byte at an even address. So that means that the D0 to D7 the lower byte will be transferred. In the same manner, read or write byte at an odd address, you need to select the BHE bar and A0 as a 01. So that D8 to D15 the data lines may be used. That means that higher byte means that most significant byte. If we want to access the D0 to D15 lines, if you want to use the D0 to D15 lines or read write a word at an even address, you need to select the BH and A0 is 00. So when you select the BH and A0 is 00, a complete word at an even address, that means that D0 to D15 lines will be transferred from the memory to the microprocessor or microprocessor to memory. In the same way, read or write a word at an odd address. If you are choosing the odd address by putting the BH and A0 is 01, the higher byte will be transferred. If you are selecting 10 for odd address, lower byte will be transferred. So that the people are always tend to look for a even address to send the complete word from the D0 to D15. So by seeing this table, we can easily understand how the data lines will be used for a reading and writing operation for even address as well as the odd address. So there are different possibilities by selecting the combination of BHE and A0. So simply we can say bank 0 is selected for A0 is equals to 0. When we put A0 equals to 0, then bank 0 is for lower order byte and BHE equals to 0 for bank 1 is selected default. So that is for odd address, higher byte will be used in a word. Let us see here the memory map, how it looks like. So the entire memory, I have already told you the 1 MB memory will be divided into two banks. One is even bank and another one is odd bank. Each memory is 512 KB each. Some memory will be dedicated for interrupt vector table. We have a 256 interrupt vectors. For interrupt vectors, we are using some dedicated memory, and some other memory will be used for CPU operations, and some other memory used for storing the program code as well as the data code and a stack segment. All these things we just accommodated in the 1 MB memory itself. So when the 8086 has been reset, then after reset is completed, the next instruction is fetched from the memory location of FF0H. That means that this is the ROM memory location. Default we have a ROM and a RAM. The ROM information is read-only memory. All the read-only memory informations will be saved from the FF0H. So from FF0H to some extent we can use the ROM memory. After that we can use the RAM memory. So in 1 MB memory, some memory will be dedicated for CPU operations. Let us take FF0 to 5H is for initialization procedure of 8086, and from 06 to 0BH is used for 8089 IO processor initialization, and 000H to 13H is dedicated to store the vector address of interrupt vectors. That means that a dedicated locations are used for processing of a specific system initialization as well as the interrupt and reset functions. Memory will be allocated. From 0014H to 7FH used for the future purpose, particularly to design or interface the hardware and software products. So far we are not using this memory. and 000H to 3FFH is reserved for interrupt vector table. The interrupt structure provides a space for 256 interrupt vectors. So total we have a 256 interrupt vectors. So for that purpose we just accommodated some memory up to 3FFH. So each interrupt means the code segment and instruction pointer for each interrupt vector routine. It consumes 4 bytes. So for 256 vector interrupts, 256 into 4. So interrupt vector table provides 1 KB. 1 KB is nothing but 0 3FFH locations from the 00H. So like that we accommodated memory future purposes as well as the hardware and software products and interrupt vector tables. Like that we just use the entire memory. Coming to the IO addressing capability. Before we have seen the memory map of 8086. Now we just concentrate on IO map of 8086. The data lines are 16 data lines we are using. So 2 power 16 means that 65,536 IO spaces are provided to map the IO map of 8086. Let us see here, the address of an IO device must not be greater than 16 bits in size. So if we want to interface the IO devices to the 8086 microprocessor, in IO addressing capability is the 16 bits in size. This means that the maximum number 2 power 16 means that 64 kilobytes, exactly we can say 65,536 IO spaces may be provided to the 8086 microprocessor. IO devices may be accessed by the CPU. That means that the data lines are 16, so the 2 power 16 is 65,536 means that 65,536 IO devices may be accessed by the CPU. The 8086 microprocessor can address up to 64 kilobyte IO byte registers, or you can say 32 kilo words registers, or you can say 8086 can generate 16 bit of IO addresses. Thus it can address up to 64 kilobytes of IO or 32 kilo word IO locations. The 16 bit IO address space means that A0 to A15 address lines in one clock period T1 and then latched by the ALE after that upper address lines. So we have a 20 address lines. For IO interfacing we just use the A0 to A15 and remaining A16 to A19 we just configured as a 00H, but we are using A0 to A15 to interface the IO devices. Logically A16 to A19 will be provided as a zeros for IO operations. And next one is the 16-bit DX register is used as a 16-bit IO address pointer, can address up to 64K devices in indirect addressing mode. In order to access the external hardware devices, to map the hardware devices to the 8086 microprocessor, in indirect addressing mode we just use the DX register to point out the 16-bit IO address. As well as IO ports are addressed in the same way as memory locations in the based addressed mode using BX. So BX register is also used as, so IO ports are addressed in the same way as memory locations in the based addressed mode using BX. So the BX register is also used as to access the IO, to address the IO ports or to access the particular memory locations in the IO ports. So in memory mapped IO interfacing, the IO device address are treated as a memory locations in page 0, that is segment address 00H. So here in 8086 microprocessor, the biggest advantage is the memory management system. The memory will be designed as designed like a page 0, page 1 and page 2 like that. So in memory mapped IO interfacing, the IO device address are treated as a memory locations. So in page 0 the memory locations will be saved. That means the segment address is 00H. Even address bytes are transferred from D0 to D7, just now discussed, and odd address bytes are transferred from D8 to D15. While designing 8-bit IO system around 8086, care must be taken that all the byte registers in the system should be even addressed. So the engineers are always practiced to map the IO devices to the 8086 microprocessor by providing the even addressed memory, particularly in 8-bit IO system. If we are choosing odd address, then the lower significant byte will be used for first memory location and the next consecutive memory location used for a higher significant byte. So the two memory cycles are used in order to reduce the wastage of the memory cycle. the better practice is to use the even addressed memory to design any 8-bit IO system around the 8086 microprocessor. With this, I just conclude the physical memory organization and IO addressing capability. If you like this video, please share and subscribe, or at least please be comment how this video. Your comments are valuable. We always appreciate your comments and your feedback to improve our quality of the program. Thank you very much. See you again. Bye bye.